No, not last time. The last Thursday, they're over there. Um, okay, so I asked you to go home and do part C and D for this as a quiz. So do your best, turn in what you have. So I'd like to collect what you have. All right, whether or not you got them both or not. All right, I want to see what you did. So turn that in. Just bring it up to me or pass them together, and just make sure your name is on it. Let's go. Come on. Turning in to me? Yes. Right up here. Please click in for attendance. There we go. Thank you. Anybody else? Okay. You can turn in. You can't get full credit for it anymore. But, yeah. That's right. Okay. Thank you. Thank you. Okay, so that's it? No one else? You did what? Oh, okay. It's okay, yeah. Everybody good? So we only have 19 people here today? 21? All right, that's good. All right, so what I'd like to do is I would like to discuss part D. I think C was doable. C is something that I will look at in grade. If you got D, I'll consider that to be like a bonus. And I'll just see how they go. But let's discuss D. You're trying to evaluate the difference quotient for f of x was the, what was it? Square root x minus 3. And remember the difference quotient. I said you need to work on trying to memorize this, right? That's the difference quotient that we use for any function, right? F of x plus h minus f of x all over h. We said that the top left corner is the part that's the most challenging usually to figure out. In this problem, the most challenging thing to do is after you figure that out, what the hell do you do with it, right? So here's, let me write underneath this f of x plus h. Replacing x with x plus h, we get this. And now let me set up the difference quotient. My difference quotient will be the top left corner is the f of x plus h. Then we say what? Minus the f of x, which for us is just square root of x minus 3. Then this entire thing divided by h. And what did I say our main goal is at this point? Once you get to this, what's your main goal? Get that h to cancel. And with this particular problem, I'm just going to show you the approach because it's not a very natural one, all right? And once you see it the first time, from here on out, just be aware that you can do this. So we're going to multiply this ratio, this fraction, this quotient, by 1, okay? And again, the way we choose 1 is going to be kind of clever. What we're going to choose over here is what we call the conjugate. The conjugate of the numerator. So when you say the conjugate of something, what you usually mean is you've got two terms with either plus or minus between them. The conjugate is the same two terms, but with the whatever sign there is, switch it. So if this is a minus, you're going to put a plus here. If this was a plus, you put a minus. That's what conjugate would mean. And something really good is going to happen, and it comes from this property. I'll write it down here so you can see this. If you take a minus b, and you decide to multiply it times a plus b, doesn't that look familiar to you? So if I take a minus b and say, hey, what's its conjugate? The conjugate would be a plus b. And now I multiply them together, and wouldn't you get a squared minus b squared? Well, if I do that here, this entire thing here is like my a, and this entire thing here is like my b, then if my result is going to be a squared minus b squared, right, then I shouldn't have roots anymore, which is why I'm happy about it, all right? But let me go ahead and do the actual computation. So here comes the conjugate. Is that right? No, what do I need between them there? Plus, right? If they were both negative, it would become a disaster. Yeah, because you don't get that middle piece to go away like you do with when they're opposite signs. So whatever you do on top, got to do on the bottom. That's just because it's a 1, right? And now we multiply. So when I say multiply, what I mean is we take the entire numerator times the other numerator, which means we're going to expand this or FOIL it. When I take this root here and I multiply it times this root, that's the same exact root, right? Same exact thing. So they square and go away. What's left then? What's underneath the root? So x plus h. So this is all equal to x plus h minus 3. Now I'm going to show this next step. In the future, you don't have to show this if you understand what's happening here. I'm going to take this root and I'm going to multiply it times this, right? Okay, first of all, this root is a positive root. I'm going to extend my radical sign. I don't like that it didn't go out far enough there. Okay, so this is a positive root, and I'm going to be multiplying times another positive root. My answer should be a positive root, correct? Or it should be positive. So I'm going to say plus, and then isn't it just whatever those two roots multiplied together are? So times that other root, right? That's this root times this root right there, and then it's a positive thing, whatever it is. You could put both of these underneath one radical with parentheses between them, though. But I'm not going to because of the next thing that's going to happen, which is this times this, which again is the same two roots, right? But this time I have a negative times a positive, which makes it negative, which is going to kill off the other one that we just got. So it'll be minus the root x minus 3 times root x plus h minus 3. And then my last multiplication, be careful on this one, you multiply the root x minus 3 over here to root x minus 3. It's the same root, so the radical goes away and you're left with x minus 3. However, this was negative, this was positive, so it's going to be negative, and that negative must distribute. So here's the negative, and then here's what was left after I actually squared those. So I prefer to just write the radicand here, and then make my negative out here and put the parentheses, or put my negative out here and then put the parentheses around that radicand. Okay, all of this over the h times all this junk, right? Now, our goal is to try and cancel the h, isn't it? So I recommend that you do not do anything with that h other than just leave it out there. So that way it's there and available to you when you do your canceling. All right, middle terms are going to cancel. These two are gone. I'm also going to distribute the negative through the parentheses over there. I'm going to rewrite everything I've got here. So x plus h minus 3. It's the first three terms. All this is gone. What's left here? Minus x plus 3. All of this over h times all that junk right there, right? And good stuff happens up top, right? Got your x's are gone, right? You've got your 3, negative 3, and all that's left is an h, yes? And that h now will be able to reduce down to be a 1 up there, right? So on my next line, I have a 1 on top, and I have, if that h is gone, the only thing left down there were those two roots, right? And we're done. Why are we done? Because we got the h to cancel, which I told you is the entire goal of the difference quotient for us in this class. All right, let's just take a look real quick, make sure everybody followed that. Ooh. Again, I'm not going to penalize you if you did not get that, but now you know, right? Now you know how to approach that sort of problem. When we see roots, we start thinking conjugate. When we see fractions, we start thinking common denominator. All right, that finishes up this section, and I'm gonna plow ahead here because we've got a lot to do. We fell behind last time. That's why we're not having a quiz today, because we just don't have time. So let me open up the 3-2 notes. If you have any questions on homework, please reserve that till the end or come into my office. You know. Well, you should be able to do all of 3-1 now. Yeah. Okay, 3-2. Here we go. You should have the notes for 3-2. I gave them to you last time. Anybody not have them from last time? Anyone that wasn't here? Because I have some extras. No? We're all good? Okay, the graph of a function. I'm going to kill the lights here so we can. The graph of a function. A lot of this you've seen, all right? So this is going to be kind of review. Given a function y equals f of x, the graph of the function is a visual representation of all of the ordered pairs x, y which satisfy the equation. We use two-dimensional plane to graph the function. Have y'all ever heard the two-dimensional plane called the Euclidean plane? Okay, it's called the Euclidean plane, or R2. That's double struck R, capital R2. R2 is a flat sheet of paper. R1 is in the number line. R3 is three-dimensional space. R4 is four-dimensional space, et cetera, et cetera. All right? So R2 is a flat sheet of paper. That's what we use to graph functions y equals f of x. So basic old graph that you've dealt with before, y equals x squared, right? F of x equals x squared. Is this a function? You remember? Yes? Okay, we have that next thing, vertical line test coming. But this is just to remind you that these ordered pairs, when we say they satisfy the equation, they mean when we replace x with -3, the y becomes 9. So by plugging -3 in here, you get 9 on the other side, and the equation is true. So if you take just these 1, 2, 3, 4, 5, 6, 7 points and plot them, you get those red dots, right? The blue represents all the other dots if you had the time to plug them in. We don't have the time to plug them in because there are infinitely many of them. So we hope that just with a few dots, we have enough to be able to tell what it looks like, right? Well, What we're going to need to be able to do is quickly in this class look at a function like x squared and know what it looks like. And not just x squared, but many, many others. Okay, that is going to be our goal in the next day or two. Now, remember that if somebody draws something on a sheet of paper, it doesn't necessarily have to be a function of x. So we have a way of testing it. If you're given a graph of some relationship, you can determine if y is a function of x by using the vertical line test. Raise your hands real quick. Vertical line test, you seen it? Okay. Here's what it says. If any vertical line intersects the graph more than one time, then this is not a function of x. So let's look at these. Which of these is a function of x? So how about A? Is A a function of x? Okay, if I draw vertical lines, I never hit it more than one time, right? So it's a function of x. Remember we talked when we first started talking about functions, I said sometimes you can look at them as functions of y instead of functions of x, but we don't do that in this class? Yes? If you wanted to do that instead, you wouldn't do a vertical line test, you would actually run a horizontal line test. But again, it's beyond this class right now. How about this one? Is this a function of x? No. Okay, if I draw a vertical line here, do I hit it more than one time? I don't hit it at all, do I? Is that a problem? That's not the problem. The problem is if I draw a vertical line, let's say here, I hit it 1, 2 times, therefore it's not a function of x. How about this one? Kind of hard to see that. It looks like if I draw a vertical line somewhere in here, I'm going to hit it twice, doesn't it? Yeah, so this is not a function of x. How about this one? Yes. Okay, most students have no issues with the vertical line test, all right? A lot of times you just want me to put like 30 of those on a test. That's it. That's the whole test. We're done? Yeah? Okay. All right. The graph of a function is a fountain of information, all right? Just having the graph of a function, there's so many things that you can determine by just knowing its graph. For example, you can usually tell the values of the function at specific points. You'll be able to tell me exactly what the value of the function is at, let's say, 2 or -1. You'll be able to tell me where the function is positive. That means where the function is above the x-axis. You'll be able to tell me where the function is negative, below the x-axis. Where the function is 0, we call those X Intercepts. Where the function hits the y-axis, what do we call that? Where a function hits the y-axis? The y-intercept. For a function of x, you can only have one y-intercept. You can have multiple x-intercepts, but you can only have one y-intercept. Does it make sense why? Think about this. That's right. Let's say I told you that this function hits here and does something. Automatically right now, if I tell you that, you can say it fails the vertical line test, can't you? So it's impossible for a function to have more than one y-intercept. You may have multiple x-intercepts. You can tell the domain of the function. That means you can tell all the values of x for which that function is defined. You can tell the range of the function, which is all the outputs, all the y values. You can usually tell where the function takes on specific values. So all of that information should be there if you have the graph. So the graph is key. If we know that, we know a lot. So we're going to do this example here. And we're going to figure out this right here. All right? Y'all doing okay? Yeah? I don't mean like today, like in this class. I mean like, are y'all doing all right? Life going okay for y'all? Oh, whoa, I don't want that. I'll paste it as an image instead. Okay, first thing I want to know, I'll try and fit this all on one page. What's f of -4? And then I also want to know what f of -1 is from this graph. So I've told you this is a function. This is the function f. By the way, is it a function? It passed the vertical line test, but that was assumed because I said let's talk about this function. All right, so what's f of negative 4? So I pay attention to the x-axis. I have to pay attention to that each of these dashes is 1, right? It could be that this was 2, 4, 6, 8, 10. So paying attention to all the labeling here. Each line, horizontal line, is 1 unit up. So we go to negative 4, right? 1, 2, 3 here, and we go and we try and find the corresponding y value, which would be 2. So the first answer is 2. All right, what's f of negative 1? What is it? So I go out negative 1 on the x-axis, go up, it's 1. I didn't ask this on your sheet, but what's f of 1? Zero, 2, undefined. You go out to 1, and you look for what the function's value is. And you see this open hole. What does the open hole mean there? That means it's not defined there. The open hole down here means it's not defined there. So you're looking up and down. You're like, where's the function? It's not there, which means undefined. All right? You actually have to have a point. Now, is it okay to be undefined at a single point? Yeah, it's fine. So your function, can't handle that. We don't take Ferraris in this car wash, okay? This is a Ferrari, I guess. The number 1 is a Ferrari. But there's other things it does handle. So it's okay at one point to be undefined. What about the next thing I asked for? Where's the function positive? Now, here's another notation for where the function is positive. If I say, where's the function greater than 0? Do you agree that that's the same question? Where's the function greater than 0? Okay, so I'm going to put a question mark behind that. So, look, first thing I'm going to say is this. When you're asked when a function is positive, they're asking you for the x values that you plug in that give you positive answers. So I'm going to write this under here. We're looking for x values. So we already knew that when we plugged in negative 4, we got a positive 2, right? But if we plug in like negative 5, we get what, positive 3? Tell me all the x values that when you plug them in, you get positives out. So how are we going to say it? Aren't there infinitely many of them? So how are we going to say it? How about this? Do you agree that everything I'm highlighting in yellow here is positive? The function is positive there, above the x-axis. And then also, from here up, and then over to here, the function is positive there. And then the function is positive from here until I get to 3. Yes? And what I would like for you to now do is tell me what the corresponding x values are for that highlighted, I'll give you a hint, those highlighted intervals. So how do I say the x values between here and here? Negative 5 to negative 3? Yes? Now that's my next question. Do we include negative 5? Do you want me to include negative 5? Yeah, because at negative 5, am I positive? Yes. Okay, how about at negative 3? Am I positive? I'm 0. Is 0 positive? No. So I wouldn't want to include negative 3, would I? So I'm going to say, my answer is going to go in here, all right? I want to say everything from negative 5 to negative 3. I want to include negative 5. I do not want to include negative 3. Let's take a poll. Do you understand that? We're not done with this. That was just that first yellow section. Does anybody want to ask a question? All right. I've got like 2 people in here that said no go, so if you don't want to ask, it's fine. Maybe 1 person now. So what else? Where else am I positive? Where else is the function positive? Right here. It's hard to see my little cursor there, isn't it? There we go. Stop it. Stop it. From right there, yes, to right here. And right there is what? Negative 1.5? Convince me. I don't believe it. It looks like negative 1.5? Yeah, but I need to know exactly what it is. It could be, right? Doesn't this little segment here look like a straight line? Okay, what's the rise over run from getting from this point to this point? I go up 1 and over 2. I'm sorry. Up 2 and over 1, right? So up 2 and over 1. That would be the same as going up 1 and over how much? Half. I'm using the slope of the line to convince myself that that's halfway. Now, if I had curved that line, you wouldn't be able to tell me, all right? All right, so I'm going to say from, where's that, negative 1.5 to where? 0. Do I want to include negative 1.5? No. Do I want to include 0? No. So I say union, negative 1.5 to 0. Remember, I said when we're looking for when the function is positive, we're looking for x values. The x values that you plug in that spit out positive numbers. So that's why my answer looks like it's an interval notation. I don't like negative 1.5. Well, you know what? But yeah, that's a good question. Why don't I do this? Why don't I make that a dot so I'm convincing you, okay? All right, are we done? Okay, we've got a little bit more where we're positive. That's going to start where? 1 to 3. Do we include 1? The fact that it's undefined at 1 says we can't include 1. Not the fact that it touches the x-axis, because it doesn't touch the x-axis. It would be positive if we could plug 1 in, but we can't plug 1 in. So we do not include 1. I'm running out of space, so I'm just going to put under this union. We want 1 to where? 3. Do I include 3 or not? No, because at 3 I am 0. So there. I think that's it. That's everywhere the function is positive. All right, let's take a poll if you understand that. Students usually have issues. Oh, wait. Oh, I didn't do that part. Oh, thank you. Thank you. Yes. What about this? Duh, that's above the x-axis, isn't it? 3 to infinity. I'm glad I was getting reds over there. Thank you. Okay, well, let's discuss that. But let's first be clear that we could not have said 1 to infinity. Because of this 3 touching the x-axis, we have to break it up, right? So it's going to go union here. 3 I do not want to include, so 3, and then we're saying out forever. How do I know it's out forever? The arrow. Notice this one's a dot. This one terminated my function there. It stopped there. Here I have an arrow. The arrow implies it goes in that direction forever. And the arrow is kind of a gray area. We are assuming when I draw an arrow, I'm telling you it's going to continue that pattern that way. All right? Nothing crazy is going to happen where it's going to come back down. All right? So now the question was, do bracket or parenthesis on infinity? It's always parenthesis. Always, always. You can never get to infinity, so can't stop. Question? Yeah, then you would not have to stop. You could have just gone from 1 to infinity. So, like if your graph would have done this, like that, then it would just be 1 to infinity. Right here? Whoa. Okay, well, I couldn't shade them both in because then it wouldn't be a function. If I shaded one of them in, like if I shaded this one in, then what's the difference in my answer over here? It'd be a bracket right here. Okay? What if this one was shaded in? It would not change this at all, would it? It would not change this. What if, check this one out. What if it was dotted up here? Well, could I include 1 now? Is my function positive at 1? Yes. And so I would put a bracket here. Because it still would be positive from 1, including 1 forever. Or not forever, till you get to 3. That would be a little tricky. Oh, no, absolutely not. They do not have to be that. And we're going to study more of that when we get to 4.4. No, 3.4. What chapter are we in? 3.4. 3.4. All right, let's continue, if you don't mind. Let's now figure out where the function is negative. So where's the function negative? That means where is it below the x-axis? So let me highlight where it's below the x-axis. And I'll use, what'll come out good here? This pinkish color comes out pretty good there. It's February, we can use pink, right? That's okay? Those are the only places it's pink, right? That's below the x-axis. So how do I say between here and here? -3 to -1.5 or -3 halves. Do I include them, the two endpoints? No, because again, at those points I touch the x-axis. I don't want that. I want it to be negative, which means below. So I'm going to say everywhere between -3 and negative, I don't like 1.5, 3 halves. And then union, where? 0 to 1, right? Looking on my x-axis here. 0, 1, do I include 0? No, because I'm touching there. Do I include 1? No, but not because I'm touching, but because the function is not defined at 1. So it'd be impossible for you to say, yeah, plug in 1, you'll get a negative. Can't say that. Can't plug in 1 at all. That's it. That's the only place it's negative. Oh, also I should have pointed out that we are looking at x values here, right? So when you talk about where a function is positive and negative, your answers are the x values that give you positive and negative. Now let's look at the next question. It says, find where the function is 0. So where is this function 0? So that corresponds to the X intercepts, right? Go run around and do a quick little horses. You ever done horses? Go do horses in the hallway. You'll wake up. Right? 0, the X intercepts, right? Do I have any X intercepts here? Does my graph ever touch the x-axis? Yes, where? -3, -3 halves, 0, and 3. And those are points, aren't they? When you're trying to write your answer and your answer is a list of points, you do not use interval notation. You use what instead? A set of squiggly. You use braces instead of parentheses and brackets. If you write a set of braces, then you're saying that what I'm about to give you are points. The points are what? -3, -3 halves, 0, and 3. See the difference? We use parentheses and brackets when we're talking about intervals, which allows you to be everything in between. We use the set of braces to represent single numbers. We call these singletons. Singletons. Which leads me to another thing. It's impossible for me to go off topic sometimes. I've seen people before write 0 this way, and I've seen people write 0 this way. This is incorrect. If you're trying to write the number 0, that is incorrect. That notation means something completely different. Now, I know in the military, you do that to avoid confusing it with the letter O. But in math, these two things are not equivalent. Okay? What this means, if I say, hey, 0, then you look at it as the set. This is supposed to be my set of braces there. It's the set that contains the number 0 in it. So it's like a basket. The only thing in the basket is a number, and the number is 0. This right here represents a basket that has nothing in it. It's called the empty set. It's the set that has nothing inside of it. Totally different things. Your basket can carry numbers. Your basket can carry cups, it can carry dogs, it can carry phones. Your basket can carry whatever. If I say I have 0 in there, I'm defining a single thing that's in the basket. If I say 0 with the line through it, I'm telling you I have an empty basket. See the difference? Totally different concepts. I just don't want you to go into a calculus class and you're using this for 0 and your instructor needs to go tell you that later. All right, what's next? Domain. So what's the domain of F? I'm just going to put dom F. Again, isn't the domain X values? You're just going to need to tell me everywhere that the function is defined. Would it be the same as what? Well, let's start off. Where does this function begin? At -5. And it continues. Is it defined here? So as I move, I look up and down. I'm hitting the graph somewhere, right? I'm hitting, as I'm moving across, I'm hitting and hitting until I get to where? 1. At 1, there's nothing. I have nothing. The 1 cannot be in the domain. And then I keep moving. Now, after 1, everything, I've got function there, got function, and until when? The implication with the arrow is that it's forever. So I need to say that. Start at -5, go all the way up to 1, step over 1, and go from 1 out. So that would be -infinity to, -5. Thank you. -5 to 1. Glad y'all are paying attention. Bracket on the 5 or not? Yes. -5 to 1, union 1 to infinity. Everything we've done up to this point, right? Everything. Is the function greater than 0? Less than 0? Where is it 0? What's the domain? Everything we've done up to this point, our answers have been X values. We've been looking on the X-axis, right? The only time we're going to look at the Y-axis is when we get to range and the Y-intercept. So let's go for range now. I'll just put ranf. I'm not making up my own notation. That is something we use. So the range of F is trying to figure out what's coming out of the function. So these are always going to be your Y values. So tell me all of the Y values that come out of this. So what I like to do is start out from the bottom. When I say the bottom, I'm saying go to the Y-axis, go down, and go way down there to -infinity. Look left and right down here. Do you hit graph? Okay, start moving up. Move left and right. Do you hit graph? Not till you get to where? -1. Now when I look to the right, do I hit it? No, because that hole there, I miss it. I don't hit anything. But when I look to the left, what happens? I do hit it. So what Y value is the smallest Y value that I ever achieve? -1. Okay, that's where it starts, right? And then as I move up, look left to right, I'm hitting, right? I'm always hitting. Is it okay that I hit more than once? Yes. With range, it doesn't matter. Okay? And I keep hitting. Do I ever not hit anything the rest of the way up? How about right here? I don't hit to the right, but if I keep going, I hit, right? And to the left, I hit. So now, how about when I get to 3? I go to the left. That's the last point I hit over there, right? But to the right, what happens? Somewhere out there, I hit it. And if I go up to 4, somewhere out there, I hit it. That's how important that arrow is. It tells me that that's going to keep going up to the right. So eventually, I will hit. If I go up to 10, somewhere to the right, I'm going to hit. If I go up to 100, I'm going to hit somewhere over there. So the implication is that if I go up to infinity, I'm always going to have something out there. So how am I going to say this? Everything from, where did we start? -1 up to forever. -1 to infinity. Now you might want to be clear. I wouldn't take off on your test for this, but you might want to put the Y as an element of. I showed you all that notation, right? Just to be clear that, look, we're talking about Y values. Your Y value is going to start out at -1, including -1. And it could go all the way up to infinity. Let's take a poll and make sure. Everything I've done up to this point, are you okay? All right, good. The next thing that we're going to ask, how many times does f intersect the line y equals negative 1/2? How many times does f, I'm going to say hit, y equals negative 1/2? Right, negative 1/2? That's what I'm saying. Okay, so let's go back up to this. Y equals negative 1/2 is a line, isn't it? Vertical or horizontal line? Horizontal. Going through the y value of negative 1/2. So I'd like to come up here, I'd like to draw that for you. If I draw a line, y equals negative 1/2, there would be something, come on, you can do it. It's not going to let me. This thing's being too picky. There we go. Good enough. Do you agree that that line looks like it's about y equals negative 1/2? How many times do I hit it? 3 times. Right? I hit that graph once, twice, 3 times. Yes? Okay. The answer is 3. Do I know where? Nope. I can't really tell. I mean, I could guesstimate these, but it would truly be a guesstimate. All right. Last thing. For what values or values of x does f of x equal 2? This is the same exact question as the one above, just disguised. It's just different wording for the same exact thing. When I say f of x equals 2, don't I really mean f of x is y, isn't it? Aren't I saying when is y equal to 2? So when is the function equal to 2? Where does it hit 2, which is like a horizontal line? So if I go up to my graph, this time I'll just draw it with my own precision drawing here. It's not bad. It hits it once here. Does it hit it here? No, because of the hole. Does it hit it here? Yes, so twice. Does it hit it further out here somewhere? No, because this goes up, right? The idea is that it goes up. So 2. All right, so that's it. That's all I'm asking for that. Oh, it asks for the values. Oh, shoot. Okay, yes. All right, it hits it twice. Sorry. Can you tell where it hits? At x is negative 4, right? And x is 4. Thank you for pointing that out. So how do I say that? X is negative 4 and 4, the braces. And I'll throw the x in there just as you don't need it, but do you see the difference between the braces and the parentheses here? If you put parentheses on this, you would be saying what? Everything between those two, right? It's not what we want to say. Just negative 4, just 4, that's all. So we use the braces. Scrap that 2. We didn't need to say how many times. All right. Whoa, what happened to the voting there? Are y'all okay with this or not? We're done with this problem. We're done with this section. 3-2 was quick, huh? You should be able to handle your homework from that. We'll see. What do you mean? Are you saying using this notation?
No. Like how it says y and then the e.
Yes.
Can you put that as the domain of that, like x of e?
Yeah. Yes. And this is not subset though notation. This is subset is this like this without that little e thing in the middle.
What is that called?
This is element of.
So could you put x element?
Yes. X is an element of these two intervals. The union of these two intervals. Subset would well, we're not going to get into it. All right. That's it for that. Let's move on. Everyone should have the notes for 3.3 because I handed them out last time. All right, so now we're going to talk about the properties of functions. We look at a few properties of functions which will become very important to us as we progress through calculus. 5.4, is that right? Or 5.4. It's 3.3. And you don't have it? Anybody not have 3.3? I've got a bunch of 3.3s over here. Who needs 3.3? Just one? 3.3 is the real big one. I don't normally have these lights off like this, but there's so much visual stuff here that I'm really trying hard to stay ahead of the class with the notes, but it takes quite a bit of time to put these notes together. So I'm hoping I can stay ahead. There's no guarantees, all right? So like if somewhere in the next few weeks, all of a sudden you stop getting handouts, just realize that y'all caught up, the class caught up to me, you know? It's just, that is another thing I'm working on too, right? So it's all a work in progress. I like to create my notes based off of the homework. So I do the homework first, then I know what you need to know, and then I go and make the notes based on that. So, all right, so let's take a look at this. Functions can be broken up into three classifications. There's what are called even functions, odd functions, and then basically neither one of those. So you can have just a function. It can be an even function. It could be an odd function, or it's just not even, not odd. So what does it mean for a function to be even? It means that when you plug x into it, you get the same thing as when you plug negative x into it. So this is what it means to be even, right there. Now, what does this mean geometrically? Here's a function. This blue function is an even function. So if I plug in an x value out here, I get a y value out, right? According to what I'm saying, that should be equal to the y value that you get when you plug in that same x but negative. So on the opposite side of the x-axis, the y coordinates are exactly the same. Does that make sense? Yes? It's a mirror image. What do we mean by mirror image? So you see that in yellow? That's because I had a typo on your notes. Please fix this. So even functions are reflections over the y-axis. I think I put x-axis on there. It's on the next page. I think, is it? Yeah, so even, check this out. This is pretty cool. Just to show you some of the power of the program that I use for this. All right? That's an even function, right? Because it is a mirror image of itself over the y-axis. So I'm going to, this is on a sheet of paper, right? I'm going to pop it into three-dimensional space now. Do y'all see this in three-dimensional space? Yes, we're looking at it kind of from the side. Y'all see that? I'm going to take it and I'm going to rotate it around the y-axis, and it is itself. Right? That's what we mean by mirror image of itself over the y-axis. That cool? This function, to be even, means that it's a reflection of itself over the y-axis. The y-axis is right here, right? So if I take this blue and I mirror it over this to this side, it would lay right on top of the other side. This was me trying to explain that in a 3D version, where I take it and I just pivot the whole thing around the y-axis. The y-axis is this axis straight up and down. If that helped, it did. If it didn't, then it doesn't matter. It was fun for me. I got to code this. Where are my computer science people? There was a few of you in here, right? So there's the code to make that happen right there, to make this picture. All right, so that's what an even function is. Odd functions work a little different. Odd functions say, function is said to be odd, not weird, okay? Odd, even, different thing. So odd if, look at this, plugging in the negative is not the same as plugging in the positive. Plugging in a negative gives you the opposite. So let's see if we can make sense out of this. This blue function right here is an example of an odd function. So look what happens. If I plug in an x, right, it's not the same as plugging in the negative x, is it? They are the same distance, right? The y values have the same length, but this one is positive and this one is negative, isn't it? So what we're saying here is that plugging in negative x, here we go, gives you this y value, is the same as plugging x into the function, but then what? Changing its sign, which would take that green thing and what? Flip it down. I'll go up there. This y value and this y value are not the same, are they? But to make them the same, I could take this one and flip it over. So just make it negative instead. So look at that equality up there. It's saying if I plug in negative x, I can get the same answer by plugging in x, but then I have to change the sign to flip it over. So odd functions, you'll have to correct this also. It's in yellow. It's a correction. So odd functions are reflections over the origin. Even functions are reflections over what? Y-axis. Odd functions are not reflections over the x-axis. They're reflections over the origin. What the hell does reflection over the origin mean? It means you first reflect over the y-axis, then you reflect over the x-axis. So let me see if I can get you to visualize this. This is an odd function. Okay? To what? Oh, over the y followed by the x. Even functions are simple. It's just a reflection over the y-axis. You're done. So check this out. Here we are in two-dimensional space. The y-axis is straight up and down. We're going to pop it into three-dimensional space. And the first thing I'm going to do is reflect it about the y-axis. Here we go. When I reflect it, the blue one is the original function, okay? When I reflect it over the y-axis, those aren't the same, are they? But now I'm going to take that answer, that black part, and I'm going to now pivot that over the x-axis. And when I do that, boom, my answer is right on top of the original function. So anytime a function looks like itself reflected twice, it's odd. They're harder to identify. So let me go back to this one and let me see if I can get you to see this. I'll try and do it up here. If I take this right side, okay? If I take that right side and just mirror it over here, is it going to be right on top of that one? No. But then if you rotate around the x-axis, will it? Yes. Question? No? Now, the reason this is going to become useful to us later is we're going to have functions that we know they're odd or we know they're even. Okay, we're going to know that to start. Like when you get to pre-cal, the sine function is going to be an odd function. The cosine function is going to be an even function. These are trig functions like sine waves, cosine waves. Okay, so they each have properties. So when we're working with them algebraically, we know that for sine, if we plug in a negative, we can get that negative out of there, turn it to a positive, but then we have to change the function negative. Or if it's an even function, where is it? If we have a negative inside the function, we can just throw the negative out, make it positive. Same thing. So those will be useful. Okay, now, some other important properties of functions. The intervals where a function is increasing, decreasing, and constant. In the previous example, what we did is we talked about where the function was positive and negative, right? Above the x-axis, below the x-axis. Now we want to talk about this concept of increasing and decreasing and constant. And if I give you the definition of it, it makes you kind of like ill. It makes you a little sick in your stomach if you read it. A function is said to be increasing on the interval I if f of x sub 1 is less than f of x sub 2 when x sub 1 is less than x sub 2 in the interval I. Oh, sure. A function is said to be decreasing, on the other hand, if f of x sub 1 is greater than f of x sub 2 when x sub 1 is less than x. Okay, so let's just get to the definition, like what it means, right? This is an example of an increasing function. So look at this. If you're going to read, you know, we read books in the United States left to right. There's some countries they read right to left. We read left to right. Okay, so imagine that you are reading this function left to right, and you're looking at it like a roller coaster, right? If you're going to read this from left to right, are you going up on the roller coaster or down the roller coaster? You're going up, right? So here's the example. I'm going to move these points. Let me move them over here so you can see them, and then I'm going to make this bigger, and then I'm going to draw an arrow between them. So look at this. X sub 1 is this point. X sub 2 is this point. Do you agree that x sub 1 is smaller than x sub 2? Yes? Okay. To go up as I move to the right means that the function's value here, right, f of x sub 1, has to be below f of x sub 2, which is what this is saying. F of x sub 1 has to be below f of x sub 2. That's what it means to be increasing. So you have the algebraic way of saying that, and you have the visual of what's happening. It's basically like a slope is positive as you move from left to right. Yes? Okay. Now, decreasing works the same way, except that the inequality is flipped over. So instead of the x sub 1 is still less than the x sub 2, but now f of x sub 1 is what? Above f of x sub 2. And if you do that, then your slope's going to be negative, so you're going down. So a roller coaster, you're going from left to right, you're going down. You know, everyone's got arms up and screaming. And then the most boring is the constant function, which means what? What did constant say up here? F of x sub 1 is equal to f of x sub 2 no matter what, which means that you're not changing, right? The heights of the functions are just going to stay the same. So you've got this happening, which is sometimes when I look out at some of my classes, not this one, I visualize brainwave activity to be somewhat, no, I'm just kidding, I'm kidding. Yes? Well, let's just keep going. Let's see how this is going to come into play, all right? But everyone understand the concept is, you know, increasing is going up, decreasing is going down, constant's flat. Let's not make it more complicated. The reason why I wanted to give you the visual wasn't because you can't understand what going up and going down is. It's I wanted to try and tie the x1, x2 to the actual mathematical statement up here of what's happening.
Is that interval I or L?
I. It's I. Standing for interval. So let's keep going. Okay. Determining where a function is increasing and decreasing. So you don't get to see all these pictures in yours, right? I mean, they're there, but you don't really get to see what's going on. I'm giving you an example of a function here, x cubed minus 4x. By looking at that, does it look like it's even or odd? It does look odd, doesn't it? Or it doesn't look like either one? So if I reflect this over the y-axis and then over the x-axis, would I get the same thing I have here? You have to convince yourself, okay? But this is odd. That was just the side note. This is an odd function. Now, I want to talk about increasing, decreasing. Do you agree that this is where it's increasing? That didn't come out too good. It's supposed to turn green. Do you see it turn green here? Anywhere I'm here, I'm going up until I get to the top, and then everyone's like, and then everyone goes down, right? You get to the bottom, you're going down, and then you start going up. So the green part is where I'm going up. So when I talk about the interval where f is increasing, we again go back to the x values. And we try and figure out the x values where it's happening. So way out here, If I look down and I start reading to the right, am I going to be going up or down? So take a point over here, go down, get on your graph, which is way down there, and then start going to your right. Are you going to go up or down? Looks like you're going to go up, right? All the way until you get to where? What x value? Somewhere in here, right? It's hard to tell. When you get to that x value, that's where you get to the top. So I need to somehow be able to represent, tell you, everything out here all the way till I get to the top of that, right? It's hard to see from the graph. In fact, nobody in here would be able to do it easily. It actually stops at negative 2 over square root of 3. That's where it ends. Yes? You wouldn't be able to get that. But do you see how what I'm doing is I'm saying this interval from here to here. I'm telling you it's negative 2 over root 3. You want to know when you're going to be able to find out that it's negative 2 over root 3? In calculus, in Cal 1. All right? And that's what we're going to be interested in Cal 1, figuring out where this highest point on this graph is. Well, where that little mountaintop is. Okay, now that's not the only place it was positive. Also, from the bottom of this valley right here, as I start moving to the right, I'm going up. So I need to say the bottom of the valley, which happened right around here, which again I'm telling you is 2 over root 3, all the way out forever to infinity. Okay, visually, do you understand the concept of increasing and then how it corresponds to the intervals on the x-axis? Yes? Okay. Now decreasing would be that middle piece, right? And so it's a very small little interval in there that it's happening. Is this function ever constant? No? No, it's not. So the function is never constant. Oh, empty set. See, I used a little cert with the line through it. It's never constant, never flatlined. Here's another example. Just ignore this increasing, decreasing, maximum, minimum. Just look at increasing, decreasing. I want to imagine, again, moving across this and ignore this notation. What I did is I copied a lot of my code right out of my calculus notes because a lot of this is used later. So ignore this notation. All I want you to do is pay attention to the graph turning green and where it turns red. Can you tell the graph is green over there? Then it turned red. Is that hard to see? And then is it still red? Yes. And then it's still red. And then what? Goes green. So if I want to, I can even play this like a game. It's kind of fun. Right? If I'm actually on that roller coaster, right, that's what's happening. I'm going up initially, and then I start going down, still going down, right? Still going down, and then I start going up. So where is it increasing? Increasing would be negative infinity all the way till I get to something over here, right? I can't tell what it is. And that's where I'd be increasing. Also, union with what? Somewhere here to when? Forever, yes? Where am I decreasing? From there to where? So now we need to talk about 0. Yeah, does that look constant? See, this is why I'm bringing this up. What's happening at 0? See, here's the thing about increasing and decreasing. To say you're increasing means when you look at 2 points, the one to the right of you is above you. That's what it means to say it's increasing. Say it's decreasing means you go to a point, you go to the right, it's below you. To be constant means you go to a point, you look to the right, and it's what? The same. So if you go to the origin and you pick a point to the right of you, where's it going to be? Is it going to be the same? What does it look like is happening? A little bit below, right? If you believe that this graph goes like this, flattens out for just an instant, and then keeps going down, then if I look at any point to the right, it's going to be below a little bit. It will never truly flatten. So because of that, I will not have to stop at 0. I will say it's decreasing from this point, which I don't know, all the way till I get to this x value over here, which again, I don't know. Yes?
Is there a function where it actually does?
It can, yep. I think it's in your notes. We're going to do it. I give you an example. I give you a drawing. Here it is. We're going to start answering a bunch of questions on this drawing in a second. All right? I don't know if it's going to be a second, but okay, some other things. These are calculus things, but we're about to talk about them. Notice this point right here. It's kind of like if you lived in this area, right? You would be the king of the hill there, right? Like I'm the highest point around here. Now you're not the highest point on the graph, right? There's other points over here higher, but if you're just saying, hey, look, around here, top of the hill. Here, bottom, right? Bottom point, locally. It's not, if you look at way over here on the graph, there's points that are lower than you, right? All right, that brings us to this definition. The absolute maximum and minimum values. Given a curve f defined on some domain D and some other number c, then we have the following definitions. F of c is called the absolute maximum value of f on D if f of c is greater than or equal to f of x for all x in D. Whoa. That means that you are the largest value the function ever takes on. You are the absolute maximum value of that function. To be the absolute minimum means that you are the smallest, lowest point on the graph of that function. Those values corresponding to the highest and lowest are called the absolute maximum and minimum values, or called the global maximum or minimum values, or even sometimes called extreme values. All those are used by different authors in different books. So if you're an absolute max or minimum value, you're called an extreme value of the function. Now, we have the idea of the absolute maximum and minimum versus what's called the local maximum and minimum. So like if I were to sit here and say that someone in here is if we look at everyone's heights, right? We would have somebody in here who would be the tallest person in here, yes? And we would have someone that would be the lowest person in here. If we're looking at Northwest Vista College as being our entire universe of students, then the tallest person in here would be our local maximum, and our shortest person would be our local minimum. Then if we look at all the students at Northwest Vista College, the tallest person would be our global max, and the shortest would be our global min. Does that make sense? So local is just looking near you, near a certain little neighborhood. And we talked about nearness, didn't we? Like, what do we mean by near? Did we talk about that a little bit? Like, are we close to each other right now? This is a little too close for me too. Okay. This is considered close. Okay. Am I close to SeaWorld? Okay. So, like, relative to the sun, am I close to SeaWorld? Okay, so nearness is a relative thing, and it's very difficult to use that word nearness in mathematics. But we have to kind of keep going around it for a while. Unless you're a math major, you'll never really get into the true, precise definition of what nearness means. All right? For us in this class, we're just going to say near means like, whatever we want it to mean. When I go back up to this picture, when I said this point right here was the king of the hill, I meant look around it. Okay? When I say around, I mean around in this general vicinity. You know what I'm saying? Like how close do you want me to look? Can we all agree that that's kind of the king of the mountain, the highest point on that hill? Nearby? Okay. So we have local max, local min. So let's take a look at this curve right here. It starts and stops, right? No arrows on the ends? Okay. Let's look at the local extreme values. All of those points are local extremes. These blue ones. Locally, it's the highest point, isn't it? Locally, it's the lowest point. Locally, it's the lowest point. Yes? Just in this little neighborhood, you know, it's like, hey, I'm the baddest ass point right here. If you just look around the points near me, I am the lowest one, right? Let's talk about that. Yes. Uh-huh. Nope. Nothing separates the neighborhood. That's the thing that's a little confusing when we say near. Like this point right here, if you just look in this little general vicinity right in here, it's the highest point, right? If you look at this one right here in the general vicinity, it's the lowest point. If you look at this one right here in the general vicinity, it's the lowest. Now, but what about these endpoints? Isn't this guy the highest if you look around him? You can only look to the right, though. You can't look to the left, right? So in his little neighborhood, he's the highest. And in this neighborhood right here, no, she. This is a she. On that one's a she. This one's a he. That one's a she. She's the highest over there, right? Do you see that? You can't look to the right. Okay. Just to let, because our domain is cut. All right, what about globally? Global means forget all the little neighborhoods. Who's the baddest ass out of the whole function? And those two are them, the green ones. That's it. This one right here is the highest value the function ever takes on, and the value is, what, 856 or something like that. And the lowest value that ever happens here is negative 4,975. Okay? Those two are global, or global extremes. Here's another example. These functions are different. I know it's kind of hard to see that. Here are local max and mins. Here are the global ones. With global, it's possible to have a global max and a global min. Or if it's a constant function, just flat line, then the highest point is also the lowest point, which means that the global max and min are the same. Good question. How am I doing on time here? Yeah. This one right here? What about it? Yes. No, you could. No, you could. I didn't label it. I'm saying this is locally a maximum. This is locally a maximum. But globally here, that's the highest point on the entire graph. This is the lowest. Notice on this one, the one we did before, notice that our global max and global min occurred inside the function. Yes? And notice on the next example, our global max and global min, one of them occurs where? At the end point, the other one occurs inside. Look at the next example. What about this one? These are supposed to be arrows. Sorry, I couldn't put them on there. This one has a global minimum, but no global max, because it keeps going up. So you can't say that there's a highest point when the function keeps going forever. And you don't say infinity, huh? There is local max right there. Local min, but your local min is also your global min. Local min, local max, local min, local max, max. What about global? You have two global. So look, now, what's the global maximum? It's the y value. That's what we're looking at. Now, it's occurring at two different places, right? But it's the same y value. And then same thing with the global minimum. It happens at two different places, but it's the same global minimum value. So I would say here the global minimum is negative 64. The global maximum is 275. This one right here went to infinity, you would have no global maximum. This one would now turn into a local maximum. Okay, this is an important theorem in calculus, the extreme value theorem. If f is a continuous function, and I'm going to highlight this word continuous, if f is a continuous function on a closed interval AB, then f attains both an absolute maximum and absolute minimum value somewhere on the interval. It's guaranteed. It's guaranteed. But we need to discuss what continuous means. So when we talk about a function in a class like this and we say continuous, What we mean is basically you can draw it without picking up your pencil, and it's a function. So if I'm going to draw a function, that right there would be a continuous function. All right? Here's another example of a continuous function. I'm drawing it without picking up my pencil. It's both of those pass the vertical line test, right? Okay, how about this? No, that's not a continuous function because there was a jump, there was a break in the graph. I had to lift my pencil to do it. So for the class like this, continuous is going to mean there's a break, all right? You can't draw it without picking up your pencil. Well, sorry, continuous means you can draw it without picking up your pencil. So let's go back to what this theorem was saying. It said if you can draw your function without picking up your pencil, and you're going to draw it on a closed interval, which means you're going to have two endpoints, there's no way to draw it where you can't get a global max and min out of it. You have to get a global max and min. So here are some examples. So there's 2 points, right? I'm going to draw something without picking up my pencil. Here goes. I have to connect the dots, don't I? I have to. So there's one way I connect them, right? Does that have a global max and a global min? Yes. Okay, let me try it a different way. Okay. Try and connect these two together. Well, what happened there? There we go. How about this? These are the two endpoints, here and here. I connected those, right? Now I went up and then I went down, then went back up. That's continuous? Okay, and look, there are my global extremes. My right endpoint is the highest point. That bottom valley point is my lowest point. No matter how I do it, I'm guaranteed I'm going to have those two things. Take this one out of here. Connect those two with something else. Oh, just a straight line. How boring. The two endpoints are global min and global max. Now look at this one. I created an asymptote and then continued from that asymptote on. What do you think? You heard me. Yeah, I don't want to repeat that again. The extreme value theorem does not apply. Why? I'd have to pick up my pencil to draw that, right? So the theorem doesn't apply. All right, for the following function below, find the following. Let's make this a 10-minute. 10 minutes will take us 27. Let's make this an 8-minute in-class group exercise to see how much you can do of this on your own. And then I'll come through and I'll tell you what the answers are. All right? Try and make this so you can see it. Everyone has these, right? Everyone has the notes, so I don't need this up here? Right? Y'all can work off of that? Okay. Let's go. Work on speed. All right, you ready? I'm going to do this. I'm going to try and do this. There it goes. All right, so one of the biggest things here is the way that you use the notation, okay? See how much of this I can do in the time we have left. The first question is what's the domain? No, X intercepts, right? Or no, it just says intercepts, right? That means both. So what are the X intercepts? I'm going to write X intercept. How many are there? There's 3. So I'm going to be writing down the X values, right? The X values in a set of braces. Okay, and they are what? -8, -4, 7. Everybody agree? Okay. Now, what about the y-intercept? Where does it hit the y-axis? At -3. So you're actually returning now a y value. Okay, this is what we got to keep track of. Yes? That's right. That's right. Okay, so look, what I'm going to do is I'm going to highlight. If I'm highlighting in yellow, these correspond to X values. If I highlight, we'll go back to the, what's that, Valentine's Day spirit, and we'll use the pink, okay? Pink is going to be Y values, all right? So for part B, domain, I'm going to highlight this in what? Yellow. Okay, domain is going to be everywhere my function is defined. It starts out way over here, X value. This X value is what, -10? I don't care what the Y value is. I just care that the function starts there. It never has a break or a jump or never has any holes. It stops over here. What X value is here? 10. So it goes from -10 to 10? Okay. Brackets, parentheses. Brackets, because those points actually exist. -10 to 10. And that's in yellow. That's X value. X is an element. X is an element. Yep. Okay, next thing. Range. So I'm looking at Y values. So I'm going to highlight this in yellow. What's the lowest Y value I have? -6. What's the highest Y value I have? 5. Now, I also have to make sure that I do achieve every value between there. So as I look up left and right, and I go and I look at this, as I move left and right, I'm always hitting graphs somewhere. If it had a break in it, then you would have to take that out of your answer. But I do have everything in between. So I need to say, what? Negative what to what? -6 to 5. Do I bracket these? Parentheses? What? Bracket, because it actually does take on those values. And that's going to be in pink. Just to help remind you that those are Y values. Next. Where is the function increasing? This is going to correspond to X values. So I'm going to highlight where it's increasing. Here, it's increasing. And here. Right? Those are the 2 intervals where it's increasing. Let's look at the X values. The X value that it starts at is what? -10. What's the X value it stops at? -6. And we will always use parentheses on intervals of increasing, decreasing, always. All right? So it's going to be F. How do we say increasing? One notation you can use is a little arrow like that. F is increasing. Where? -10 to -6. But also, what X value did this start out down here? Ooh. I can't draw a straight line. Starts down here at 4 and it ends at 10. Union 4 to 10, 410. And parentheses on those always. So if you need to make a note to yourself, always use parentheses when you're talking about intervals, increasing, decreasing, and constant. All right? E. Where is it decreasing? So that's going to be here to here and here to here. So the X values here are what? -6 to -2, union 2 to 4. Those were X values, so I'm highlighting them. Okay, I'm going to change my increasing is going to go like this. That matches up with this. My decreasing was here to here, here to here. That matches up with this. Okay, where is it constant? That's the next question. Right? No? Does it answer? Yeah. Where is it constant? So you can go F, and then you can do like a flat arrow like this. And that's happening, I'll just circle it, right in here, isn't it? What are the x values that correspond to that interval? Negative 2 to 2, parentheses on those. Negative 2 to 2. Almost done. Part G. Part G, we want to know what the local maximums and minimums are. So here's what I recommend. For all these max and min problems, write them as points, like ordered pairs, like the x and y coordinate together in parentheses. So tell me where I have any local maximums. At what points? Negative 10, negative 6. So these are points, right? Negative 10, negative 6. Where else? Oh, wait. Hold on. Local max. Hold on. No. Positive 10. This is a local minimum. Yeah, local max. Positive 10, 5. 10, 5. That's this point up here. Do we have any other local maximums? Negative 6, positive 2. Two, negative 3. This would not be a local max because you have to be bigger than the stuff around you. This one, it's bigger on this side, but not this side. Okay? So it's like it's king of the hill, but only if you look on that side of the hill. If you look on this side of the hill, it's the same stuff. So is that all for local maximums? Which one? 10, 5? I'm looking at this. Remember, these are points, okay? These are x and y coordinates. These are not intervals, okay? So if I go out to the right 10 and go up 5, that point corresponds to a local maximum. This one right here, negative 6, 2, I go to the left 6, up 2. How about local minimums? There's that negative 10, 6, negative 6. Anywhere else? Right here, this one. 4, negative 5. That's it for locals. What about global, which is H? So what is the global, I'm going to say G max, and then G min. So the global max happens at the point 10, 5. The global minimum happens at negative 10, negative 6. Now, if somebody asks you for the global maximum of the function, having the point is acceptable to me, all right? But when you talk about global max, you're actually asking what's the value, what's the highest value it ever takes on, which would be 5. So if you just put 5 here, that would be okay. But I prefer you just put the point. And the global minimum would be negative 6. That would be fine. If you just put the y, it's fine. I like the convention of using the point because it also tells you where it happens. Not only what it is, but where it happens. It takes on a value of 5, it happens at the x value of 10. I hope that helped. So we still have in 3.3 more to do. Okay, we're going to finish that up next time. So on your homework for 3.3, let me tell you what you can do right now because you can't do it all. So for the 3-3 homework, this is page, doesn't have the page, sorry. The only thing, 25, 27, 31. Those are the only ones that are out of that section that we've talked about. Let me see, 25, yeah, 27, and then 31. Pardon? Yeah, that's for 3-3. You can do all of 3-2. Does everyone know that this schedule, I mean, you should know by now, this schedule for your homework is on our website. You need to print it out. If you need me to make a copy for you, I can. All right? That's it. Make sure you turn in your clickers. Have a good weekend. I did not. Let's, well, I can't do anything about it, but what I will do is I will make a note in here that you're okay. What's your last name again? Okay, and today is the 5th. Okay. Okay, what's your last name? We're so gotcha. Okay, thank you.